up here right now.
We need to build an escape vehicle.
It needs to recognize different things and navigate.
Let's look for parts. Hey guys, I just found an Android tablet.
I found a Raspberry Pi.
Hey guys, I found this abandoned car with a full battery. What's this?
Isn't that an SDM? Let's escape with this.
So I found an Android tablet. You?
I found an SDM.
And a robot.
And an RPi.
Oh, then how can we escape with this?
Okay, so I'll use the Android tablets to place the obstacles as we see them and communicate that to the RPi using Bluetooth. Once the RPi finds these obstacles, it can send these messages based on which we can display different things on the RPi. For example, mapping the image ID to the images on the arena. The Android will also serve as a place to send commands to the RPi, such as to start exploring the arena and start navigating the maze.
So I will train an image recognition model using YOLO to recognize different things that are out there. And from there, each object will have its own image ID, which will then be sent to the Android tablet.
Then I will use the RPi to handle the communications from all the different components. Then I will use the camera connected to the RPi to take images and send it to the image recognition server.
Starting with the Android, obstacles are sent to the Raspberry Pi. The Raspberry Pi listens, receives, and forwards them to the algorithm server. The server listens, receives the obstacles, calculates an optimal path, and sends it back to the Raspberry Pi. The Pi listens, receives the path, and sends movement commands to the STM. The STM listens, executes the movements, sends an acknowledgement back to the RPi. Then the Pi captures an image, sends it to the image recognition server, which processes it, detects the object, and returns an image ID to the Pi. Finally, the RPi sends the image ID to the Android, which updates the app display.
So what do we have to do about the algo? I think you can find a shorter path to escape. Okay, how about the obstacles? We don't know what's out there. Or remember, if I found a tablet, you can give us the information about the obstacle. And then I can input the algo, then I can find the shortest semi-tonal path between each obstacle, which can help us to escape faster. Okay, then how will the robot receive our algorithm? I think we can connect to the RPi through IP port connection. That's good.
First, we calculate the absolute distances between obstacles using the x and y coordinates before applying an appropriate weight multiplier. We then take the shortest path from all permutations. The algorithm will then plan a route that ensures the most number of obstacles visited in the shortest time possible.
Okay guys, so the STM will have to know where it is and where it isn't.
Now, the physical components are connected to the STM through various I/O pins indicated with the IOC file. One of the more interesting challenges were the soldering of the wires that connected a socketed connector of the STM32 board with the IR sensors. Next, we will focus on the communication required for task 1.
Our robot receives instruction from the Raspberry Pi through UART communication. The receive command is stored in buffer, where the first character defines the action, S for moving straight, R for turning right, and L for turning left. The second character defines the direction, whether moving forward or backward, and the subsequent characters represent the magnitude of the action. The STM interprets these commands and performs the requested action, and then sends an acknowledgement back to the RPi via UART. And this is done repeatedly in order to command the robot to move as the algorithm commands it to navigate, and allow the Raspberry Pi camera to take the necessary pictures for task 1.
Our approach for task 2 involves using the ultrasonic sensor to detect and stop before obstacles. To ensure precise and dynamic tracking of how far the robot has traveled, we store the encoded values for left and right wheels. Our robot executes a calculated sequence of turns, such as move car right and move car left. They are carefully adjusted using preset angles to ensure the robot turns around obstacles precisely. Functions like move car left correction help to make adjustments in the turning to navigate even more accurately. The IR sensors help with this turning by detecting a safe distance from the obstacles before initiating the turn. Here, the robot has turned back and is facing straight to prepare itself to enter the car park. A final 10 degrees is executed to position the robot such that it will move diagonally towards the car park. The total distance traveled is calculated using the encoded data, ensuring it moves back the same distance. The robot stops as soon as it detects its boundaries, completing the task.
Hey guys, do you remember the times when we fried our STM 4 times? Do you remember how much solder we had to go through to solder the wires for our IR sensor? And oh my god, the times whereby the STM code was corrupted when we uploaded it wrongly.
You know that time our RPi did not have enough resources and we had to use multi-threading to solve the problem.
We really went through a lot last time. I couldn't recognize a lot of the images and had to use a lot of augmentation and made a lot of images from scratch.
No, I really had to dig deep into the Bluetooth libraries to solve the issues with the Bluetooth thread completely hanging. And that really taught me a lot about how Android is with Bluetooth.
Do you remember the challenges we faced? They're good.
Yeah, remember the robot used to stop and not move after moving. I think it's due to the greedy search.
Oh. Yeah, but I think we solved that by reducing the safety space.
Yeah, that finally solved the problem for us.
Thanks for watching, guys.